Okay, so now just like before, this tells us about the low temperature approximation of this one-point function. So we just have the matrix elements multiplied by the Boltzmann factor. Now the one-point function is not modular invariant, but it's modular covariant. The operator transforms under the modular transformation. And so we have some transformation like this. And so now that translates into this high temperature expression for the one-point function. Okay, and so now the matrix element, these powers here, and this exponential. Okay, a very simple generalization or analog of the Hardy formula. And so from this, now we can read off the high energy asymptotics of the average OBE coefficient. So we're going to take the OBE coefficient average over all states of a given energy. And so we write this one-point function, sum over energies, weighted by the density of states, Boltzmann factor, averaged matrix element. And then just by equating this to the previous expression and doing some inverse Laplace transform, and then just a little bit of work, you get this asymptotic expression for the average one-point function. Okay, so this expression is expressed in terms of proportional to that matrix element, the dimension of the operator you're looking at, the dimensionality of this lightest operator chi that gives a non-zero one-point function, and well, the expression's a little bit more complicated than simple. One notable thing about this actually is that this, if you look at this for large energies, it's either the minus something, we have the energy here, and so this average OB coefficient actually decays exponentially at large energies. Which you think about is actually not something you expect in the generic quantum field theory higher dimensions. So not even expectation values of operators in energy eigenstates with decay exponentially. Here it's coming from the modular invariance of the two-dimensional CFT in this case. But its property, actually think of it as in more detail, it's really a property of the average. And so you can kind of convince yourself that in individual states, the one-point function could be, would not necessarily be decaying, it could be growing, but the average one is guaranteed by modular invariance of decay. And I think that's like an interesting point when you're trying to understand bulk physics, because there could be large things that are averaging out to small. Okay, so we'd like to, again, understand this result from a bulk point of view. So again, we'd like to take the large central charge limit, and in principle, we could keep this delta chi dimension to be arbitrary, but let's actually just assume it's order 1, and so this means that this delta chi is going to become like a light operator. So we take that limit, and then we get this expression for this average one-point function. So now we get a fairly simple exponential. So this is the result we'd like to explain from bulk. We can come back to dropping this restriction later, but not quite simple. So okay, so what do we do? So the basic logic is somewhat similar to what I talked about before. So on the bulk side, we want to compute the one-point function of some operator. So we want to look at the Witten diagram for a one-point function. And now we're at finite temperature. And so at finite temperature, of course, you have the CFT on the torus. And as we know, when you're looking at high temperatures, you fill in that boundary torus by the bulk geometry, which is the BTC black hole. Okay. So we're looking at some Witten diagram computed on a BTC black hole background. And so now we're going to incorporate this non-zero matrix element. So this non-zero matrix element corresponds to some 3-point coupling in the bulk. So we have some cubic coupling. So to each operator associated a field, phi sub O or phi sub chi. We want this cubic coupling like this. This is what would give rise to a non-zero matrix element. So I have to build up the one-point function using this cubic coupling. And so here's the kind of diagram we have. So we can have the bulk boundary propagator for this field corresponding to the one-point, the operator of the one-point function. And now the new thing is that the chi field that's produced by this cubic vertex can now wind around the black hole. Okay? In fact, the entire contribution comes from the winding. So if it doesn't wind around the black hole, you're going to get 0 because if it doesn't wind around, remember the BTZ geometry is locally ADS, so it doesn't wind around, it's basically just seeing pure ADS, and then it's zero by the fact that one-point functions vanish in ADS by conformal variance. So in general, this thing could wind any number of times around. You should sum over all the possible windings. But if we're interested in leading asymptotics for large E, so the energy E is the energy of the black hole. So when you have a black hole of energy E, its horizon radius is given by R plus like this, and the horizon radius, of course, is growing with E. So the asymptotics, the horizon is getting very, very large, and so it costs you a lot of action to wind around. And so the leading asymptotics are given just by winding once around. Okay. So, so you can evaluate this diagram in the large energy limit, just having a winding once around. And in fact, we do this more carefully, but here's the upshot of that. The leading approximation comes from, well, here's the cubic coupling. This factor here, delta O L reg, is just the length of this geodesic going down to the horizon, regular horizon all the way. This factor here is, so 2 pi r plus is the length around the horizon, and it's weighted by the dimensionality of the chi field, weighted by the dimensionality of this guy's winding as usual mass, basically. And so you just translate these expressions back into the CFT language, and indeed you get back this result that followed from the CFT result. Okay, so that works nicely, and it's kind of nice. You can see the length of the horizons are coming out naturally here out of the CFT calculation. It's not just the entropy coming out, like in Party's form, it's actually the length of the horizon, because it's being measured by this particle it has to wind around. So that exponential here doesn't contain Newton's constant, it just contains the length of the horizon weighted by the dimension. So that means you're seeing the geometry of the horizon. And
on the boundary, it's below temperature, right? So why let the temperature affect the period from the upside point of view?
Well, because we're looking at high energy states. So we're looking at, so what we're trying to compute here is the matrix element between high energy states averaged over all the states of a given energy. So if I ask you, how do I describe it in the bulk? How do I describe a correlator that's averaged over many high energy states? Well, I'd expect that's going to correspond to a black hole, right? A black hole represents the average of a lot of high energy states. Yeah, so it's not that it's not a temperature directly coming in here, but we have high energy states. And so it's like, I'm asking about something like the microcanonical ensemble. And so, in fact, I'm thinking about a black hole as having a definite energy. So the fact that it's a temperature is really a separate issue. It's the energy. The fact that it's a high, typical black hole represents the ensemble of typical high energy states. That's what it is.
Is it theoretically an assumption, or is it something that?
Yeah, it's an assumption.
And then you know what your state is.
Well, it's an assumption. It's not, well, it's built in the sense that I assumed, on the CFT side, I was assuming that this was non-zero. And if this be non-zero, the dual statement is that there is a cubic coupling. Yeah.
So essentially, you're just calculating an OP coefficient. Chi.
Yes, yeah, exactly. That's why exactly. It's the essence.
You're assuming this is the first you calculated first, now it's vanishing.
Yeah, the leading
Chi being a very heavy state.
No, chi is a light state, but it's no. So
O is a heavy state.
E is a very heavy state. E is a very heavy state. And, but now we're expressing by modular invariance, the asymptotics of these OP coefficients with large E are expressed in terms of OP coefficients at small energy.
Oh, I see.
That's the idea. So it's like in the usual party formula express high energy states, low energy states. Here we relate high energy asymptotics to low energy coefficients.
So that's where you use the functional invariance.
Exactly, yeah. Really high energy stuff to low energy stuff. Now you can actually push this further, and instead of doing any approximations, we can ask now about how do you attack a full conformal block. And so in this case, we're looking at, let's say, we call these torus blocks. And so when we think about computing the full thermal one-point function, again, there's a conformal block expansion of objects like this. So we have a trace over all states. We can break up that trace in all states into the trace over one conformal family plus trace over another conformal family, et cetera, et cetera. The trace over each conformal family is what defines the global torus block. Okay, so the global torus block is, and everything global is actually going to do this now for some, think about things in global conformal algebra, break up things perfectly for that. That's actually what we understand at this point. And so the global torus block means you take this trace here, but only sum over one primary and its descendants, but otherwise compute this Boltzmann weighted sum. Okay, that's the global torus block. Again, this is a quantity which again is fixed by the conformal algebra. Okay. And so you can work out what this is. Again, it has some expression in terms of hypergeometric functions and so on. I'm not going to write that down here. But the nice thing, this again is a simple formal description. So it's the picture's almost the same as what I drew before. The difference is now we're not actually doing this whole expression here without making any assumption about beta being large or small. And so, so I draw this picture again of the black hole. I have some winding around the black hole. But now, what I'm going to do here is, before I actually I was doing some asymptotics with high energy, and so what happened was this geodesic, in the previous case, the black hole was getting very, very large, and so this geodesic effectively just hung very tightly close to the horizon. I wanted to minimize that. But if you're at generic temperature, not necessarily large, then that doesn't happen, and so you should take this diagram here and integrate this vertex everywhere with all of ADS. And these lines here would be the full propagators. So you're evaluating the full one-point width diagram, but in one topological sector. One topological sector means you're going to wind once around the black hole. The full correlator would correspond diagrams like this, but like a single winding, double winding, triple winding, etc. All windings, but only some over one winding, and then compute the width diagram. Just integrate over VTZ, bulk propagator for a single winding, bulk boundary propagator. Then you can show this is exactly equal to one of these corresponds to reproducing this hypergeometric function results. Okay. And then you can imagine going further through this one correlators, and that's stuff that we're working at right now. Okay. Yes, I'm basically done. So in conclusion, so the output of this is that, yeah, it seems that conformal blocks, these basic building blocks of correlators and CFT, themselves have very nice bulk gravity representations. And I think this will be, so you could say everything I've done here in this talk right now is basically stuff that's fixed by symmetry. Okay, so you can say where's the physics. I view this as going to be a useful tool going forward. You definitely want to go as far as you can and figure out everything that's determined by symmetry works on the two sides, and then you can start going after dynamics. So again, I hope to try to address that paradox I mentioned at the beginning in terms of these ideas. So the two things were the conformal have this nice gravity representation. Modular invariance allows you to compute asymptotics matrix elements. And okay, so one general thing going forward is that everything I did in the bulk at this point was like classical. It was like true level diagram or classical physics. And this was related to the fact that when I looked at the Virasoro blocks, I took C to infinity. In fact, I was just looking at the leading behavior, say in the 1/C expansion. And that's what we reproduced by some classical gravity calculations. But on the CFT side, you can work out results 1/C expansion. In fact, in principle, you have the results, exact results at finite C. And the 1/C expansion in the CFT should correspond to the loop expansion in bulk, right? Because 1/C is like Newton's constant. So in principle, there's a lot of, say, quantum gravity data hiding in these Virasoro blocks that you can work out, and you'd like to be able to reproduce that in bulk. And eventually, what you really want to understand is how to formulate an exact statement. What is the bulk quantity you should compute to get an exact conformal block at finite C? That would contain, you could say, non-perturbative quantum gravity information. If you had such a thing, if you know how to formulate such a thing, then that's where you could really go back and I think resolve this Malvazina paradox, because you could look at some 2-point correlator on a torus, that's like the 2-point function of finite temperature. And order by order, the one over C expansion, I expect that this decay down to 0 will occur and there'll be information loss. But if you really have finite C, and you take T large, then the correlator will decay, and it should then start doing some interesting stuff. And if you figure out what that onset of interesting stuff, if you can translate that CFT behavior into the bullet description, I think that would be essentially the same as saying, here is the quantum gravity effect that restores information. So this is a fruitful direction. And that was all good.
I don't know how relevant my question. In four-dimensional gravity, of course, black hole has a serious problem, information like non-neutrality and singularity. But BPG black hole has no such problems.
No, it has really the same problems, actually. The information paradox looks basically the same for three-dimensional. So
Then my question is whether it is reflected to the conformal block representation of the BPG or
yeah, no, the special thing in two dimensions is that we have the central charge appearing in conformal blocks, and the central charge is related to gravity. In higher dimensions, that goes away because I already have a finite dimensional conformal algebra. So I still have the same information paradox in the bulk, but how that will be related to CFT effects is different. It's unclear. So I don't know exactly what to compute in the CFT at higher dimensions to address the information paradox the same way that I do here in the history case.
There's other attempts to try to understand the quantum properties of the top, like entanglement entropy. We are seeing connection of this with Kraus.
Yeah, I mean, the one point of intersection is that you compute entanglement entropy by computing correlators and twist fields, and then you can, since you can be correlators, you can think of those correlators in a conformal block expansion, and you can apply that technology. Now, that's sort of a technical point, but how, these larger things about people trying to use entanglement entropy and quantum information and so on to study the horizon. I mean, it's hard to, at this stage, it's hard to make the connection to that. And those ideas are, I know that. Other than think about computing entanglement entropy through twist correlators.
I guess you can compute the four-point function using that to the.
That's what I'm saying, exactly.
Yeah.
So that's what I'm saying.
This is almost the Rich-Canadian form or something.
Yeah, exactly. So you can prove, there's a nice paper by Hartman where he showed that you could actually establish, you prove your sort of assumptions of CFT, you could derive the root Hakinagi formula from CFT. One more question.
People have taken the large C limit in the context of logarithmic CFTs. Is there any relation?
In the context of what?
In the context of logarithmic conformal
logarithmic.
fluids.
Actually, I said nothing about logarithmic CFTs. There was a question.
related, but could you imagine doing the same in the double algebra higher spin case? Like, is our understanding of conical defects only?
Yeah, and I can definitely imagine it. If I got some week done, if I had extra time, I would have discussed. There's a nice story there where you can, yes, the answer is yes.
Would it give you a more precise correspondence with?
Well, it's not important, right? It's a generalized version. So now you're looking at more general solutions that have like conical defects with higher spin fields turned on and so on, broke by more general operators. So there's a nice story. So all the same ideas go through. It's just it's richer and they are larger to double algebras and so on. But the basic idea is still.
But even the story of the scalar going around the DZ canvas also.
Yeah. So there it's expressed in terms of like we have formulas now in terms of like working the Chern-Simons formulation, and there are Wilson lines. You talk about Wilson lines winding around cycles and so on. So not all this is worked out, but it's definitely generalizations.
So I have a couple of questions myself. So first one, have you considered like what to do with the super conformal blocks?
No, we haven't got an idea. So
do you usually in ABS CFT super conformal symmetry component compact? Right? Because the RAM was super symmetry, it's all compact.
yeah.
Do you think it might also be
Yes, I mean, that's right. So if we have the, right, so with the additional global symmetry algebra with the rotation of the sphere, yeah, you shouldn't expect that there would be
Yeah, it
something
really kind
happening
of
on
work out, because
on the sphere.
there's people studying conformal field, super conformal field theory, that's also very hard thing to get.
Yeah, yeah.
Yeah, now you actually give a kind of nice geometric picture, like as long as you know the propagate.
It would be very natural, yeah, just like,
Do your business.
yeah, just like we can compute Wilson loops that, you know, use
Yeah.
on sphere, yeah, expect
And
that.
there's another related question, is that recently people have been looking at Van amplitudes, and that's actually related to what I was asking now, you're really summing over all the possible channels. But the amplitude itself is a lot simpler than the conformal block, which you have a hypergeometric function, but many amplitude actually using a simple ratio, it's like a rational function. Do you have any feeling about what a natural geometry object? Because van amplitude, the way you cook it up is a very complicated thing. It's like you have to go through this max decomposition and so on, and there are only very few data points that we know so far. I was wondering if there's some intuition like on this side. Like,
Well, yeah, I mean, this picture here is very much tied to like position space. So here we get nice pictures in position space, but the formulas are complicated, whereas in the known space, formulas are simple, but you're working in this other space.
but then again, van amplitudes seem to emerge very naturally.
Yeah, no, they're totally the nice there. To make the explicit results look the nicest, the Mellon algorithms is the way to go. So, I mean, yeah, you hope there was some mixing of these two sets of